I already started.
Okay. So it is a pleasure to introduce Maria Elenice Rodrigues Hernandes, who will talk about Hamiltonian vector fields with its symmetries. And thank you very much, Elenice, for accepting the invitation. You can start when you're ready.
Well, okay. Thank you very much for the organizers of this seminar. It's a great pleasure for me to talk about this work that is not it's not exactly the theory that we study, but we start to try to study this with Patrícia and Eralcilene. And what's our purpose in this work that was published in Bulletin of Brazilian Mathematical Society this year. Its purpose here is to obtain normal forms of a class of Hamiltonian vector fields when we consider some definition, semisymplectic action of a Lie group, and we consider symmetries and reversing symmetries of the vector field. We define each element here in this talk in order to understand what this context and what the techniques we use to solve this problem. Well, Hamiltonian systems is a classical object that study, especially in physics. Hamilton gave a reformulation of Newtonian mechanics, and this new reformulation was called Hamiltonian mechanics. And these dynamical systems describe a lot of problems, especially, for example, the evolution of the planetary systems or the evolution of an electron in an electromagnetic field, etc. And we can, in a classical way to present an Hamiltonian systems is to consider a function from R to N to R. And the Hamiltonian system is to the first derivatives of the first n equations of these systems is to consider the partial derivative of the map H with respect to the n and last variables, xn plus 1 to x to n, and the last n equations are minus the partial derivative of the map H with respect to the first variable x1, xn. Or in a simple matrix notation, we can rewrite these systems as a product of this matrix that we denote by J, the gradient of the function 8. So this is the classical Hamiltonian system. And the study of this kind of systems was possible to develop another interest of mathematicians, like the development in symplectic algebra and or symplectic geometry. And now you try to put the definition, we not consider more systems of differential equations, but the vector field defined in terms of an Hamiltonian function. And what's necessary to introduce the elements that we need to introduce to define the Hamiltonian vector field? Well, in a context of the linear algebra, a symplectic, we need to consider V a real vector space of finite dimension and omega a bilinear form. And to define a symplectic vector space, we need to consider bilinear forms with two properties. That omega is skew-symmetric. That means that the omega uv is minus omega vu, and this bilinear form is non-degenerate. That means if omega uv is 0 for all v in v, we obtain that u is 0. And another way to rewrite the non-degenerate definition is possible to prove that the bilinear form is non-degenerate if and only if its matrix is invertible. So this is the hypothesis that's necessary to define a symplectic vector space. So a symplectic vector space is a vector space with a bilinear form that is skew-symmetric and non-degenerate. Okay, and there is a classical result in this theory that say that if you have a bilinear form that's non-degenerate and skew-symmetric, there exists a basis of the vector space such that the matrix of this bilinear form is exactly the matrix J, the same matrix that appear in the classical definition of Hamiltonian systems. So, if you have a symplectic vector space, there exists a basis of the symplectic bilinear form such that the matrix is exactly the matrix J. Okay, this basis is called a symplectic basis, and with this result implies that the dimension of the vector space, a symplectic vector space, the dimension is even. So this is the classical bilinear form in R2n. In this case, with this definition of the bilinear form, the canonical basis of R2n is a symplectic basis. And the canonical symplectic space considered in the literature is R2n with this bilinear form. This is the canonical symplectic space. When you consider this bilinear form for n is equal to 1, that is in R2, from R2, we can illustrate in more details. This bilinear form in R2 is precisely the product of xw minus yz. This is a bilinear form that is given by determinant of these matrices. It's simple to verify that this bilinear form is skew-symmetric, is non-degenerate. The matrix of this bilinear form is invertible. And when you write this bilinear form in matrix notation, we see that the matrix J is the matrix, the canonical basis is the symplectic basis. That is, the matrix of this bilinear form in a canonical basis of R2 is the matrix, exactly the matrix J. Of course, we can, in R4, we consider not the canonical bilinear form, we consider other bilinear form in which the matrix of this bilinear form in the canonical basis of R4 is this. That's not the matrix J, is another matrix. And this illustrates the canonical basis in this case is not a symplectic basis, but perhaps with a permutation of the vectors of the canonical basis, we obtain, that is, there exists another basis of R4 in which the matrix of omega is exactly the matrix J. Okay. And of course, when we study to structure, it's natural to study the maps that preserve this structure. If we have two symplectic vector space, a a linear map is called the symplectic if is a linear map from V1 to V2, preserving the bilinear form, the respective bilinear forms. That is omega 2 phi u phi v is equal to omega 1 in u and v. So phi is symplectic if satisfies this equality, and a map phi is a symplectomorphism if is symplectic and is an isomorphism. So when we study symplectic vector space, it's possible to prove that any symplectic vector space of dimension 2n is symplectomorphic to canonical symplectic space that are 2n omega 0, where omega 0 is exactly the bilinear form that we defined before. So with respect to symplectomorphism approach, you don't have any other special. All symplectic vector space is symplectomorphic to this classical R2n omega 0. And we can rewrite, it's not only we can define the symplectic vector space not over the linear algebra point of view, but in the study of manifolds, change the vector space by a manifold, change the bilinear form for a two differential form, two differential form, and the properties of skew symmetry and non-degenerates we change by the two form is closed and non-degenerate. So we can rewrite these results in terms of manifolds, also in more general context. So with these definitions, a classical Hamiltonian vector field study very much in the literature is to consider the symplectic vector space R2n omega 0, and the Hamiltonian vector field is the vector field that can be written as the matrix J gradient of the function 8, the Hamiltonian function 8, and J is this matrix. 0, identity, minus identity, 0. This is the classical object. There are a lot of works in the literature that start with this symplectic vector space, and a lot of properties of the matrix J. For example, the matrix J satisfies the J square is equal to minus identity, that is the inverse of the matrix J is minus J. We can define the symplectic group as the classical group defined as the invertible matrices in GL2N satisfying these two equalities. B, J transpose of B is equal to B transpose J, B that's equal to J. It's a classical group in algebra. For example, some relations that is very used is the property that if you have a matrix in the symplectic group, if and only if the transpose of this matrix is an element of the symplectic group, these are only some elements that we can, properties that a lot of results in symplectic algebra use strongly the properties of the first property, J square is minus J square is equal minus identity, and the properties of the symplectic group and its Lie algebra is obtained by this special situation. But what the definition of the Hamiltonian vector fields for a general omega bilinear form? how we can define the symplectic group if here we don't have the matrix J, but we have a general matrices of the associated Hamiltonian function. All these things, it's what we explore in this work. Our study provide number forms for Hamiltonian vector fields with symmetries, when you take into account the symmetries and the matrix. We consider that the matrix of the symplectic form may possibly be different from the matrix J of the canonical symplectic form. But why this study is interesting if we know that all symplectic vector space is symplectomorphic to R2N and the matrix J. Why is different to consider another matrix that's not the classical? One of the reasons I'm trying to convince you that one of the reasons that we study vector fields take into considering the symmetries and the versing symmetries of the vector field. And perhaps the symmetries of the vector fields may not be preserved by symplectomorphism. There are a lot of things we study in the same object. And another reason is that there are some works in the literature that study Hamiltonian vector fields for other classes of matrices different from J. Here we list some of them. There are older results in 1971 until more recently in 2017. Some of these works consider there are some applications in physics. For example, Schiffer's, this last work, and another has a more approach with respect to the dynamical systems, mathematical viewpoint, etc. But there are some works, several works in the literature that study Hamiltonian vector fields for other classes different to J. So it means that it was interesting to study this class. And of course, vector fields with symmetries, there are a lot of results. Here we put only the Hamiltonian vector fields, in which in these works they study Hamiltonian vector fields with symmetries. And I think all of them are involving symmetries. Yes, I think yes. And these lists of reference illustrate that can be interesting to know, to study Hamiltonian vector fields for in a general context, in the sense that the matrix of the bilinear form is not the matrix J, and on the other hand, to look the symmetries involved in this problem. But how we can define Hamiltonian vector field in a more general context? If you have a vector space and a symplectic vector space, omega is a bilinear form that is skew symmetric and non-degenerate, and H from V to R, a smooth function. The definition of omega Hamiltonian vector field associated to this function is the unique vector field that we can write to this form. The matrix that appear here is not only the matrix of omega, but is the inverse of the matrix of omega. We transpose this matrix times the gradient of the function 8. This is the general definition of Hamiltonian function, and the classical is when this matrix here is J. 8 is called the Hamiltonian function, and we can, in this study, Patrícia, Eralcilene, and myself, to study Hamiltonian vector fields in the general sense, we need to study all the symplectic algebra involved in this problem and what the difference we have with respect to the classical one. So, for example, once we can define the symplectic group with respect to this bilinear form. It's not it's the same, but it's not exactly the same we have in the classical symplectic group. We call the omega symplectic group the set of matrices, invertible matrices, satisfying the transpose of B, the matrix of omega, B is equal to omega.
The same means isomorphic, right?
Yes, we mentioned after that it's isomorphic.
I guess it's canonically isomorphic.
Yes, it's isomorphic.
Not only isomorphic, it's canonically isomorphic, right?
Yes, canonical isomorphic, yes.
And then, okay, sorry. Bye.
This symplectic group satisfying that if the matrix omega satisfying the similar property that the matrix J, that's the J square, satisfies exactly this property. J square is minus identity. If the general matrix omega satisfies the matrix omega square is minus identity, we have the definition of this symplectic group exactly the same we define the canonical symplectic group. SP and R is exactly defined to this way, where here we have the matrix J. So when our matrix satisfying this property, we recover all properties that we have with respect to the canonical symplectic group. And of course, we prove that this group is isomorphic to the canonical definition of the symplectic group. So, but there are some results in this contest that was proved different from the proof when we have the matrix J. We characterize its Lie algebra, what's the result we can recover or not, etc. But okay, if you study the symplectic vector space, we have an action of a Lie group on V. Here we put the classical definition of the action of a group on a vector space. Okay, we have a differential map. It's not necessary, not need necessarily the condition to be differentiable. Perhaps we need only continuous map. Perhaps not necessary we put the same definition that we obtain in a manifold context. If for it given an action, we have a map that associates for each element of gamma, we consider rho gamma diffeomorphism from V to V induced by this action. That rho gamma x associate gamma times x, the image of the orbit of the element x. If rho gamma is a linear map, var phi is a linear action, and for each linear isomorphism, we associate a matrix. So when we have a linear action, we associate rho gamma a matrix, invertible matrix in GLM. Okay, but if you have a space and you have an action of a group, we can study the what's happened with the bilinear form under this action and what's happened with the vector field with respect to this action. So the classical definition in this theory is that an action, is this definition, an action of a group, Lie group gamma on a symplectic vector space. This action is called sigma 1 semisymplectic if there exists a group homomorphism sigma 1 that associate to each element of gamma 1 or minus 1 such that the bilinear form in differential of rho gamma u differential of rho gamma v on x is sigma 1 gamma omega uv. That is, if sigma 1 of gamma is 1, we say that for any element of gamma, we say that this action is symplectic. For an element gamma, if for one element gamma, we have sigma 1 is minus 1, gamma is antisymplectic element.
Elenice, could I interrupt again?
Yes.
The point is that if you have this kind of action, right, then you should you have this, if you said that there is a canonical isomorphism, right, then you have what happened to a vector field by that action. Then you pull back to the canonical isomorphism, apply the canonical action, and then go back. Is it okay? It's the same, right?
It's the same, yes. We not use this language, but it's exactly the same.
Because this is just natural, okay.
Yes, we respect to pull back, not so to define all this.
Universal transformation from one to another one, okay.
Yes. We decide not to put in this language, not to define all these objects, because this released all what means the pullback by this.
Yeah. Maybe it could be more complicated. This I don't know.
Yes, because this, of course, is the general language that you can put in a more general context, but we decide to put this in order to be more explicitly, which means
because then sometimes you could have germs of vector fields who are equivalent in the first sense and not equivalent in the, but it's normal. It's somehow just it what happens. But it's somehow interesting that the action doesn't have open orbits, right?
Yes.
If it doesn't have open orbits, then it could be just a sort of move of the orbit spaces. Okay. Mm-hmm.
Yes.
Okay. Thank you.
Thank you again, Lev, for your comments. And a vector field, right. With respect to the vector field, the action is, we say that a vector field is gamma sigma 2 equivariant if there exists a group homomorphism sigma 2 satisfying that the vector field in an element rho gamma x is sigma 2 gamma, the differential of rho gamma applied to x of x. So when sigma 2 for an element gamma is equal to 1, we have a symmetry. When gamma is a symmetry, when sigma 2 of gamma is minus 1, we have a reversible symmetry or antisymmetry. And if for all elements in the group gamma, sigma 2 is equal to 1, the vector field is called gamma equivariant. And we not use sigma 2. If sigma 2 is trivial, that means the sigma 2 is 1 for all elements of gamma. We have a gamma equivariant vector field. So with all these objects, Alomaier and Montaldi showed that in a symplectic vector space, there are 4 types of symmetry for Hamiltonian vector fields. That's an element of the gamma of the Lie group is called the symplectic variant if with respect to the bilinear form sigma 1 is 1 and is in symmetry with respect to the vector field sigma 2 of gamma is equal to 1. If a symplectic element with respect to the bilinear form, but is a reversible symmetry with respect to the vector field, we denote as R, and similar definitions for unsymplectic equivariant is unsymplectic with respect to the sigma 1 and sigma 2 is equal to 1, and unsymplectic reversible that the both homomorphism is equal to 1. But in this work, Alomair Montaldi consider describe these 4 types of symmetries, but in his study, they study only one case of when we have, I don't remember very much, but I think they consider symplectic and an element that is reversible. So in this example, our group is the product of the group generated by the matrix tau, that's defined here, times Z2 psi, that's the group generated by the matrix psi, and this group acting on R4, where the matrix of omega is given to this way, and when we try to verify, we prove that this action is semisymplectic. And what are the elements that sigma 1 sends to the 1? It's precisely the identity Y4 in gamma and Y4 and psi are the elements that when we done this computation, sigma 1 is equal to 1. And what the elements are symmetries or reversible symmetries. In this case, symmetries are the identity, again, Y4, and the matrix tau and the matrix psi are the symmetries. So here we have the 4 types of symmetry: symplectic equivariant, symplectic reversible, unsymplectic equivariant, and symplectic reversible. So this example illustrates all these possible types of symmetries that can appear when we study a symplectic vector space. Well, but normal forms in the context of vector field, it's a classical study in the classical way to obtain a normal form of a vector fields with this approach is to consist in performing change of coordinates around a singular point. And we assume here that the vector field is given as a formal power series, and we consider perturbations of the identity. In it, we have here a homogeneous polynomial of degree k, with the property that this change of coordinates preserve the linear part of the vector field. It's very interesting when they study dynamical systems because they preserve the eigenvalues, etc. And the another property that's we want to eliminate terms of degree greater than 2 in order to obtain another vector field in a more convenient way, or preserving the properties that we want that the normal form need to have. There are a lot of methods. There are some methods that provide normal forms, like Belitsky, that reduce this problem to the computation of solutions of a partial differential equation. Elfick et al. Provide an algebraic method in which it's possible to obtain a normal form choosing nonlinear terms that commute with the action of this one parameter group S. Here, L is the linearization of the original vector field. Here, this bar means the closure of the set. And Baptistelli, Manuel Izeri, they used the theory of algebraic invariant theory with the approach of Elfick et al. In order to present a method to obtain normal forms of a reversible equivariant vector field for any vector field that preserve the symmetries of the original vector field. And in this book, Shou, Li, Wang, 1994, they present a normal form of Hamiltonian vector field, in the case of Hamiltonian vector fields, but not considering symmetries, and they show that the normal form can be obtained by means a normal form of the associated Hamiltonian function. So here we have these two elements here. We have an Hamiltonian vector field, and we study symmetries. What the difference here? Well, what we use here is to mix these two approaches, because is in some sense is more simple to obtain a normal form of Hamiltonian function, and from this normal form we naturally to obtain a normal form of the vector field. More simple than, for example, presented here, that in our case, the vector fields is a particular case in which the vector field is defined in terms of the Hamiltonian function. And if you have a normal form of this function, we obtain a normal form of the vector field. But all this study, all the tools used here, used in the method of Elfick, was important to describe the symmetries and reversing symmetries in the Hamiltonian context. So here I propose to obtain a normal form for Hamiltonian vector fields in which the normal form have the property that the vector field is Hamiltonian, and the symmetries of the original vector are preserved. For the first, for this purpose, is sufficient to consider symplectic diffeomorphism. If the diffeomorphism is symplectic, the normal form is obtained is an Hamiltonian vector field. And when we consider gamma sigma equivariant diffeomorphism, we have the symmetries of the original vector fields are preserved. With these two conditions, under the change of coordinates, we have preserved what we want to preserve. That's Hamiltonian and symmetries conditions. So we start again. Consider an Hamiltonian vector field. The map H is a smooth germ with critical point at the origin. H0 is equal to 0, and L is the linearization of the vector field. That's the differential of X at the origin. We consider Taylor series expansion of the map H. Here we have each 8k is an homogeneous polynomials function of degree k. And when we associate to this homogeneous, to this polynomial part, the vector fields associate to this 8,2 plus 8k, it's possible to prove that we have a Hamiltonian function associated to this homogeneous part, x, this notation, x, when we put the function 8 here, 8k, means the matrix, this exactly the same, this matrix times the gradient of the function. So it's possible to prove that we have a Taylor series of the map H. The associated vector field have the same linear part of the original X, and this linear part comes from to the vector field associated to the polynomial of degree 2. And when you consider symplectic diffeomorphism, in order to preserve the, what is a symplectic diffeomorphism? Symplectic map is, we put again the definition of symplectic map. What is a symplectic diffeomorphism? For each k, given a polynomial element of degree k, there exists a neighborhood of the origin and a symplectic diffeomorphism such that C can be written to this form, whereas we have here a Hamiltonian function, Hamiltonian vector field associated to this function Ck. That's exactly defined to this way. These are the diffeomorphisms that we need to consider in order to preserve the Hamiltonian condition, the Hamiltonian vector field. A normal form that we obtained before is also an Hamiltonian vector field. So the symplectic diffeomorphism preserve the linearization of the vector field, and we obtain a new Hamiltonian vector field associated with a new function. That's the composition of H with this diffeomorphism. Okay, but here, what happened if we consider the new vector field induced by the diffeomorphism Xi? So if we fix k, we go jet by jet. For each k, we have a homogeneous polynomial. We want to preserve the first k minus 1 elements, and we want to know what's happened with the homogeneous polynomial of degree k. So if we consider a symplectic diffeomorphism to this form, the differential of this diffeomorphism is identity plus the differential of the Hamiltonian function associated to Ck. The new Hamiltonian vector field is formally conjugated to X, in which the linear part and all terms of degree k minus 1 are preserved. And what's happened to the degree k? What appears here is the original Hamiltonian function of degree k minus the Poisson bracket of the map Ck and the element of degree 2 in the Taylor expansion of 8. This part is what we provide a linear part of the vector field. And what is the definition of the Poisson bracket of two functions? If you have two functions, the Poisson bracket of f and g is a function that is defined as the bilinear form applied to the xf in the element x, xg in the element x, where xf, xg are the associated Hamiltonian functions to the functions f and g. So with this, we control what happens when we apply a change of coordinates, because we know precisely what happened. We preserve we go jet by jet, k by k, preserving what we obtained before, and we change the element of degree k to this form. Okay, so this Poisson bracket, it's an element that we can define, associate to the quadratic form A2. We define a linear map from that send a polynomial element of degree k and another polynomial element of degree k given by Poisson bracket of Ck A2. And with this definition, we consider a decomposition of the polynomial functions, the polynomial set of polynomial functions of degree k in the image of the linear map ADK A2 is difficult to read, but this image of this map with dk, that's a complementary subspace in pk of this set. dk is exactly the subspace we need to describe in order to obtain a normal form. This result is not our result. This result we can see in the book Show, Lee, and Wang. And for a canonical symplectic space, R2n omega 0. And when they show that if you have a symplectic, here we put in our contest, if V omega is a symplectic vector space, and X is an Hamiltonian vector field, X is formally conjugated to an Hamiltonian vector field given to this way, where, what's the difference here? The difference here is that we write the new function. K is a normal form of the function associated to the maps. We have a original vector field, X. X have an Hamiltonian function, 8. We compute the normal form of 8. We write this normal form to this form, to this way, 8 squared. We preserve the original quadratic form of the X, of the vector field X, and plus K3, Kr, where normal form means when K, each element of degree K, belongs to this complementary subspace. Well, we need to explain again because there are a lot of things to say. So, what we done? We have original vector field. We have an Hamiltonian function. How we obtain the normal form of the Hamiltonian function? If we write a new Hamiltonian function as the original quadratic form, the quadratic form A2 is from the original vector field, plus some elements in which for each k, this element belongs to this complementary subspace, we have a normal form of the function k. And associated vector field to this function is a normal form of the vector field. So the vector field is formally conjugate to this way. So it's in some sense, it's a good technique in order to obtain a normal form of the vector field, because we obtain a normal form for functions, and as consequence, we obtain a normal form for the vector field. Here, we put here the definition of the normal form. So the question is, according to your purpose, for example, what property do you want with respect to the normal form? We need to characterize this complementary subspace. As in our case, we study symmetries and reversing symmetries, we will want to determine which are our complementary subspace in order to obtain a normal form, preserving the symmetries and reversible symmetries in our context. I don't have precisely our time, but you tell me if and how minutes I have. And what I need here is to determine what we need now is to determine our complementary subspace decay. Okay, for this, I promise that the last definitions, P sigma gamma is the set of gamma sigma polynomial invariant functions. In polynomial invariant functions means that with respect to this action that appears sigma gamma here, that can be 1 or minus 1. And this set is a model of the ring of invariant polynomial functions. Invariant means that the homomorphism is trivial. All element sigma, for all element of gamma, sigma of gamma is 1. So this set has a structure of a model over this ring. We said before that when we obtain normal forms appear naturally this group S, we need to assume in our case that the action of S is symplectic, because when we have a classical canonical symplectic space where we have the matrix J, this group, the action of this group is symplectic. It's symplectic. We don't have another possibility. But when our matrices of the bilinear form cannot be J, we have example in that this action cannot be symplectic. So we need to assume these hypotheses in order to obtain a normal form. Another thing is that we have a semisymplectic action, and we have two homomorphisms, sigma 1 in order to have a semisymplectic action, and sigma 2 to study symmetries and reversing symmetries of the vector field. So sigma 1 is associated to the bilinear form, and sigma 2 is associated to the vector field. So here we present our result. For obtaining this result, we add the definition, we add the hypothesis that our Lie group is compact. This definition is here. This hypothesis is important because we use techniques that come from some results of Golubitsky or some results of Miriam Manuel, Patrícia, Iris, and the others. And we use, for example, a concept called the normalized Haar integral. And for this integral, the hypothesis of compact is important. And for other questions, but essentially because the proof of this result, we use the normalized Haar integral. So gamma for us is a compact Lie group. Sigma 1 and sigma 2 is a homomorphism that we defined before. X is an Hamiltonian vector field. X sends 0 to 0, and L is the linear part. We can assume that the action of gamma on V omega is sigma O semisymplectic, and X is gamma sigma 2 equivariant. So if the group S, the action of S is, sorry, if X acts symplectically on V omega, so the vector field is formally conjugated to a normal form, where normal form means that its homogeneous polynomial part of the new Hamiltonian function belong to this set. Of course, there are some technical definitions here. We try to be so quickly. Pk means polynomial functions of degree k, and sigma 1 tilde, sigma 2 tilde is a new homomorphism where with respect to the group that the symmetries involved here to the normal form is not the symmetries with respect to the group gamma, but S direct sum with gamma. And the action is defined to this way. It's a technical definitions, but what's important here is that we describe precisely this set in order to obtain a normal form of the associate function, and as consequence, we obtain a normal form of the vector field. So this set, with all these conditions, is the set of invariants. K need to be invariant with respect to the S direct sum of gamma. Well, we will illustrate this with an example. If you have a diagonal group generated by the matrix that rotation of P2 and a rotation matrix, and kappa is a reflection, acting on an arbitrary symplectic space. The matrix of the symplectic space is given to this way. This constant is different to 0, and L is the linear part of the vector field is given to this matrix. Well, it's not difficult to verify that the group D4 acts sigma semisymplectic. In this case, sigma 1 and sigma 2 is equal, so we denote the both by sigma. The vector field with quadratic form given to this way presents two types of symmetry. There are four types that can be appear. In this case, appear only two types of symmetry. The rotation matrix is symplectic and equivariant, and kappa is unsymplectic and reversible. And in this case, this is the set that we need to describe in order to obtain a normal form. The group S in this case, I forgot to say that the group S in this case is isomorphic to the rotation group, SO2. And this set, Pk, is precisely the polynomial functions of SO2 generated by x1 squared plus x2 squared. So the normal form of the normal form of the function 8 can be written into this way, where appear the generator x1 squared, x2 squared. And it's easy to obtain if you have a normal form for the map K, for the a normal form for the map H, we have a normal form of the vector field only computing omega this matrix times the gradient of K. So here we obtain a normal form of the vector field X. So I think that's all. Thank you very much for your attention.